Hi guys, welcome back. Let's go to our third example, which is a driver and a seat suspension system. In this example, we are going to learn how we can handle a spring that both ends of the spring are moving, okay, and dampers where both ends of the dampers are moving. So let's get into it. Okay, I don't know if you guys have seen any of these car seats before. If you open them, inside the seat, you see that there are a lot of coil springs. Also, if you have seen, there is cushion inside them. Okay, so what we will do is we lump the effect of all of those coil springs into one spring element and we call it as K2. Similarly, we can somehow simplify the cushion as a damper. Okay, in this problem, we're going to simplify this as a viscose damper and we call it as B2. How realistic is this model? Well, this is a story for another day. For now, let's get the very simplified model. Also, I do not care about the size, the gender, or the race of the driver, so I would lump the effect of the driver in one mass element, and also I would lump the effect of the mass of the seat in one mass element, M2. And at last, for the suspension of the seat, I would consider a spring and a damper as well, a linear spring and a linear damper, basically a dashpot, okay? And these two guys are basically connected to the cabin floor here. In this problem, the assumption is that the displacement and velocity is provided from the cabin floor, and we want to model this system. Okay, let's get into it. What I'm going to do is first, I'm going to list the elements in the system. Yes? So, let's start with the inertia elements. I have two inertia elements, M1 and M2. If you guys remember, this is a mechanical translation system. And for that specific reason, the masses are my inertia elements. Then let's go and model the stiffness. What is the stiffness element in my system? You see that I have two springs, K1 and K2. So let's go ahead and put them here. And also for the friction element, you see that I have two dampers, which are B1 and B2. They're both viscose dampers. So B1 and B2. What is the source that makes the system run? Well, the velocity and displacement from the road surface. Okay, so the source is in fact external displacement and external velocity. And if you guys note that, it's basically a source of current. Yes, it's a source of external velocity and external displacement. And at last, we want to know how many ODEs we have. And for this problem, since we have two masses, we can say that, well, there are two ODEs. And we said that we're going to change this, that at the end of this chapter, that with the number of masses, we're going to end up with ODEs. This is not completely accurate. For now, let's say that with the number of inertia elements, we're going to have ODEs. Okay, let's go to our 4-step approach. Yes, step 1. Is selecting our coordinate system. Okay. Now, if you notice, I have two independent motions basically in this problem. And basically I have three independent motions, okay? But one of them is from the source, the cabin, yeah? So I have Z0 Z1 and Z2. If I assume that Z1 and Z0 and Z2 are measured from the static equilibrium, as the origin, then I know that I can neglect the weight in my free body diagram. Okay, so my assumption here is that all of these guys are measured from the static equilibrium. And I'm just going to use the same coordinate system that the problem setup gave me, okay, which is pointing upward as the positive direction. Okay, good. At this point, I'm good to go. My coordinate system is known. I know the origin and the positive direction for that coordinate system. Now, let's go to step 2, which is basically isolating my inertia elements. What do I mean by isolating them? I mean that grab them, disconnect them, and throw them on a piece of paper. So I'm going to grab them, I'm going to disconnect them, and I'm going to throw them on a piece of paper. Just to make my life a little bit easier, I'm going to show the coordinate system on top of these guys as well. So this is going to be Z2 and this is going to be Z1. Yes? Good. Now, let's go to our next step. Step 3 is the heart of my solution, free body diagram, or FBDA. If you guys remember, there was a sequence of forces that I would go after. Few, CSR. Well, let's start with the friction. Do I have a friction force? Of course I do. I have one damper in between mass M1 and M2, and I have one damper between the floor and the car seat. So, for the friction force, I need two things. I need first the magnitude and also the direction. Okay? And if you guys notice, both ends of, for instance, both ends of the first damper and the second damper are moving. So, how can I find the correct answer? How can I find whether the friction force, the magnitude, is B1, Z naught, Z dot 1 minus Z dot naught, or B1, Z dot naught minus Z dot 1. You see that? The order here is first Z dot 1, the order here is first Z naught. Which one I would choose? And also, when I selected my value, my magnitude, what is going to be the direction? Well, we are going to do this in a very systematic way. Okay? Before solving this problem, you need an assumption. It's not really important what is your assumption. Well, do not make crazy assumptions. Okay? Make reasonable assumptions, but stick to them. Okay? And for making those assumptions, we just use common sense. Okay? For example, between mass of the seat and the mass of the driver, which one do you prefer to have less displacement and less velocity? Let's say that you are sitting in your car, okay? Do you prefer you have more vertical displacement and velocity than the seat, or you prefer the seat to basically have more displacement and velocity than you, okay, but you be as stable as possible? Of course, nobody cares about the displacement of the seat. Everybody wants the driver to be as stable as possible. Yes, as stable as possible. So my assumption 1 would be Z1, which is the displacement of the seat, is greater than Z2. I want the driver to be as stable as possible. Also, I would assume that Z dot 1 is greater than or equal to Z dot 2. Where did I get these assumptions? Common sense. Yes, common sense. Let's go to the next assumption. My second assumption. And the second assumption, I would need an assumption between the mass of the seat and the floor. Which one do you guys like to have more velocity and displacement? I mean, vertical velocity and vertical displacement. Do you want the floor of your car to have more vertical velocity compared to the mass of the seat, or the other way around? Let me ask you this question. When you drive your car on the surface of a road, do you want the car to fly? Or no, you want the floor to have as less as possible vertical displacement and velocity? Well, of course, everybody wants the car not to fly on the streets, and nobody cares how much the mass of the seat actually moves, yes? So my second assumption is that my Z0, my Z1 is greater than Z0, and my Z dot 1 is greater than my Z dot not, or equal to. Yes? Okay. Now, look, these assumptions are not really important. We use common sense to make these assumptions, okay? But the important thing is you stick with these assumptions. Anytime your assumption is violated, your system, your model, your free body diagram will take care of it, okay? Now, let's work with these two assumptions here, okay? What I'm going to do is I'm going to use second part of this assumption, okay? Well, I wanted to model the damper B2 between the mass of the seat and the mass of the driver. So this is my B2. Yes? Okay. So what I would do here is I would always select somehow the order of the velocities in a way that inside the green parentheses here is always positive based on my assumption. My assumption here is the velocity of Z1 is greater than velocity of Z2, okay, or M2. So I would select it as Z dot 1 minus Z dot 2. With this assumption, okay, inside the parentheses is always positive. Similarly, let's go here. I know that there is a friction force between the floor and the car seat, okay? So this is B1 and parentheses, if you guys remember. I would select inside the parentheses always positive. I would select the order in a way that inside the parentheses is always positive. So here I assume that Z dot 1 is greater than Z dot naught, okay? And I will select it as Z dot 1 minus Z dot naught. Always inside the parentheses positive, based on my assumption. Where did I get those assumptions? Common sense. Okay. Now I need to figure out the direction of these guys. The magnitude, I figured out. Now I need to figure out the direction. For figuring out the direction, I would ask you guys to grab a pen and a hammer. Okay? And pin the mass that moves less to the wall or to the ground, or just make it stable. Yes? Make it not move. Let's go and do this. Between M1 and M2, I assume that M1 is actually moving faster than M2. So M2 is the one that moves less or slower. What I'm going to do is I'm going to grab my pen and my hammer, okay, and I'm going to pin this one to the wall so it's not moving. Then I'm going to move M1 in the positive direction of Z1. Yes? So I'm going to bring M1 a little bit up. If I bring M1 a little bit up, the damper by nature is a friction element. It's going to oppose that direction. Okay. So if the distance between the two elements are getting closer and closer and closer, the damper is actually opposing that motion. Yes. And this is how we get the direction of the damper force. Good. Next one, between M1 and the floor, which one was slower? Well, we assume that the floor is moving slower than the M1, yes? Okay, so we fixed M1, we grab the pin and the hammer, okay? And we pin down basically the floor to the wall, okay? We make it not move, and then move M1 in positive direction, Z1. If you look at this, when M1 goes positive direction, Z1, the distance between the two guys, between the floor here and M1 increases, yes? So the damper is opposing that relative motion. It's gonna pull them back together, okay? So let me just make this one with green. So we have a little bit of consistency here. The damper is gonna oppose that direction of motion. Good? Okay. So we are done with the frictions. Externals, we didn't have any external forces. Weights, if you guys remember, we neglected the weights. Why? Because the origin of our coordinate systems were selected from the free lengths of from the static equilibrium point, not the free length of the spring. The next one is contact. We do not have contact, or we didn't model contact in this problem. The next one is the spring. Again, you have two springs. One spring is here between the driver and the car seat. The other spring is between the car seat and the floor. So you have one spring here and one spring here. Yes? You need to figure out the magnitude and the direction. Again, guys, it's going to be always like this. You make inside the parentheses positive based on assumption. Okay, so you see that both ends of this spring are moving. Okay, so it's important that to make inside the parentheses positive based on your assumption. Here, you assume that Z1 is greater than Z2. So inside the parentheses, it's going to be Z1 minus Z2. Here, you assume that Z1 is greater than Z0. So inside the parentheses here is K1, Z1 minus Z0. Always make inside the parentheses positive. Yes? Now, you need to figure out the direction of these guys. Yes? For figuring out the direction, grab a pin and a hammer and pin the one that moves less to the wall, move the other one in the positive direction. Yes? So between Z1 and Z2, Z2 was the one that moves less. Okay? So what we are going to do is we're going to pin M2 or the driver to the wall. Okay? And we're going to move M1 in positive Z1 direction. Now close your eyes for a moment. Imagine that you pin M2 to the wall and M1 is moving closer to M2 in the positive Z1 direction. Do you think that the spring is in compression or in tension? Of course, it's in compression. When it is in compression, is it going to push or is it going to pull? Well, you guys tell me. Of course, it's going to push back. Okay, now let's remove the pin. Do the similar thing for the spring down below. Between M1 and the floor, we assume that the floor moves less. Yes? So we're going to fix floor. We're going to pin floor down to the wall. Okay? And we're going to move M1 in positive Z1 direction a little bit. Close your eyes. If floor is fixed and you move M1 upward, do you think that spring K1 is in compression or in tension? Well, it's going to be tension. It's going to be stretched. When it's stretched, it's going to push or it's going to pull back. Well, of course, it's going to pull back. Okay. And you guys note that I do not need these two. They're action and reaction forces. Okay. Because I didn't have any mass there. Okay, so this is in fact my free body diagram. Okay, I'm done with the spring forces. There are no ropes in my problem, so I'm done with the free body diagram. I can safely navigate to step 4, which is equations of motion. Okay, so let's go ahead and write Newton's second law for forces along Z1, which are equal to M1 Z1 double dot, and the forces along Z2 equal to M2 Z2 double dot. Okay, so let's look at the forces along M1. How many forces do you see? I would see 1, 2, 3, and then 4 of these guys. Yes, and if you look at these 4 forces that are applied on the mass M1, you see that all of them are applied at the negative Z1 direction. Yes, they're applied downward, which positive Z1 direction is pointing upward. So it means that all of these guys are negative. Yes, similarly, if you look at the forces that are applied on the mass M2, let me just show them with another color. Okay, you see that these 2 forces are applied in the positive Z2 direction. They are applied at the same direction of Z2. Okay, so let's go back to this guy. Okay, the forces that are applied on the mass M1. So this is going to be negative K1 Z1 minus Z0, negative B1 Z1 dot minus Z0 dot, negative K2 Z1 minus Z2, and also negative B2 Z1 dot minus Z2 dot. They are the 4 forces. All of them are in negative direction. So this is going to be M1 Z1 double dot. Yes. Similarly, for the forces that are applied on the mass M2, you see that you have only 2 forces, okay, and they are both positive direction. They are K2 Z1 minus Z2, yes, plus B2 Z dot 1 minus Z dot 2 equals to M2 Z2 double dot. Okay, now what I'm going to do is I'm going to keep the inputs on one side and bring all the dynamic terms to the other side. Yes, so look at this. I can distribute this K1 here and here, and also I can distribute this B1 here and here. Okay, somehow I can dissect the input velocity and input displacement, okay, and keep these guys on one side and bring all the dynamic terms to the other side. Why do I do that? Because I need to do the sanity check. I need to make sure that my solution is correct. Okay, so if you distribute there in the first equation, I'm going to write it down here and down below here. Okay, it's going to be K1, oops, it's going to be K1 Z0 plus B1 Z0 dot equals to, bring everything else to the other side, flip the signs, yes? So M1 Z1 double dot plus B1 Z1 dot plus K1 Z1 plus K2 Z1 minus Z2, and then plus B2 Z1 dot minus Z2 dot. Okay. And also for the Second equation, I do not have any inputs here. I just bring everything that has a dynamic variable inside it, okay, to the other side, flip the signs, yes? So it's going to be 0 equals to M2 Z2 double dot negative V2 Z1 dot minus Z2 dot negative K2 Z1 minus Z2. Yes? Good. Okay. Sweet. Now, let's call these equations as equation smiley and equation cyclo. Okay. Let's look at the equation smiley. How many families do I have in equation smiley? Well, I have family of Z1 and family of Z2. Yes? In the family of Z1, in equation smiley, I would have three members, Z1 double dot, Z1 dot, and Z1 itself. Okay? And you see that there are no sign mismatches within the members of this family. Similarly, for the family of Z2, I have two members, Z2 and Z2 dot. Both of these guys are negative. There are no sign mismatches within the members of the family. So I'm good with equation smiley. Let's go to equation cyclo. Again, I have two families, family of Z1 and family of Z2. Z2 has three members. Family of Z2 has three members. Z2 itself, Z2 dot, and Z2 double dot. And if you look at this, you see that Z2 double dot is positive, Z2 dot negative multiplied by negative, it's positive, and Z2 itself negative multiplied by negative, it's positive. No sign mismatches within the members of family Z2. Similarly, for family Z1, you see that I have two members, Z1 and Z1 dot. Both of them are negative. There are no sign mismatches. I can safely box these two equations and report them as my final model. You note that these two equations are linear because every term in these equations is linear. The order of equation smiley is second order because you're dealing with the second order highest derivative here. And the order of equation cyclope is second order as well. Yes? So in total, the order of this system is fourth order. If you found this video, make sure that you subscribe to the channel for more physics-based modeling problems and follow the full series as we build our way towards intelligent control and autonomous systems. Thank you.